Once again, welcome to Cambridge A-Level Physics. Our topic is, we are still under dynamic. Our topic tonight, 3.3, Principle of Conservation of Linear Momentum. My short form, P for principle, O for off, C for conservation, O for off, L for linear, M for momentum. Right, so this all basically summarizes for you what is conservation of linear momentum. What are some of the things you'll be covering? Right? Basically, this is what principle of conservation of linear momentum is about. Total momentum of system of interacting bodies remain constant provided no external force acts on the interacting bodies. That's the definition for momentum. This is how we write change in momentum, final momentum minus initial momentum. This definition of force, Newton's second law. This is also an alternative way of writing Newton's second law. And this is Newton's third law. Force of A of B on A equals force of A on B. Okay, you want the resources, you can visit Physics AS, where I put my notes there, and my video. Okay, or you can subscribe to Buhinku YouTube channel. These are for past year paper, AS. This paper 1 and paper 2. This one is Physics Practical, paper 3. I think most of the answer will be from before 2020. Right, let's look at the syllabus. State the principle of conservation of linear momentum. Apply the principle of conservation of momentum to solve simple problem. Include elastic and inelastic interaction between objects in both 1 and 2 dimension. Knowledge of concept of coefficient of restitution is not required. Recall that for perfect elastic collision, the relative speed of approach is equal to the relative speed of separation. Right? Recall, we don't need to show how we get this. Understand that while momentum of system is always conserved in interaction between objects, some change in kinetic energy may take place. Let's state the principle of conservation of linear momentum. POCOLM. If an object collides, the total momentum before collision is the same as the total momentum after collision, provided no external forces, example, friction, act on the system. This place you can also get the notes by the author. Right? Or mathematically, we can summarize sum of initial momentum equals the sum of final momentum. Linear means it's a straight line motion. Provided means you set a condition. You must obey the condition before total momentum is constant. No external force, or it means a closed system. Objects collide. If you want to use a general term, it's called interacting bodies. Right? Doesn't need to specify the collision itself. It can be explosion. Right? We've seen about it can be explosion, can be radioactive decay. Yeah, that's why a better word to use for object collide is interacting bodies. Or total momentum of a system of interacting bodies remain constant provided no external forces act on the system. No external force means it's a closed system. Linear means straight line motion, provided set the condition for the principle to work. Mathematically, we can write it as momentum is constant, no external force, no resultant force acting, or total momentum initially equals total momentum finally, right? Or in mathematical symbol, or you can take that across, take this across, change in momentum is the sum of final momentum minus sum of initial momentum equals it should be zero. That means no change in momentum. Collision is an incident that happens in a short time interval. Motion of the bodies before is different from that after collision. Right? Example, in this case, initially this is not moving. This is moving with the speed u1. After collision, this one rebounds with minus v2. I show a opposite direction, negative. Then this one is v2. Right? Remember, momentum is a vector. So we need to, here we choose to the right as positive, so to the left is negative. The system is considered a closed one. That means no external force acting involved. Is this a collision where you push two trolley together? It's taken from 2010 June 21 paper 2021, where you push a two trolley together. That's the spring, and then this is the frictionless ground. After that, you release it. So is this considered collision? Trolley push together to compress the spring. Right? This is just to give you the idea of explosion. Is it a short time interval? Compress the spring. Short time interval, you let go. Motion before and after. Initially, both of them are not moving. So initial momentum is zero. Final momentum is right? They are moving in opposite direction. Right? It's a closed system if there's no frictional force. Yes, it's a collision. Example, explosion, firing a gun, colliding cars, radioactive disintegration. Right? So these are the various forms of head-on collision. The colliding bodies travel in a straight line before and after collision. The bodies travel in the same, right, as in this case, same direction after collision, or it can be different direction. This one approaching each other, this one rebounds. This is not a head-on collision. Right? It's a two-dimension, which we'll study separately. Okay, that's the review from what we have learned from dynamic, momentum, time graph. Right? That's the change in momentum. That one can be velocity. If there is velocity, this is final velocity, this is initial velocity. So this is uniform acceleration. Force is just a change in momentum over time. Right? That gradient, change in momentum over the time. And this is the gradient. Gradient of this line is the force acting on the body. And if we draw the force time graph, that gradient is constant. That gradient is zero, it's zero. Right? So we're just playing with this formula now. Take this across there. F T So delta V is just this area under the graph. Okay, collision. That's the sphere A, mass MA, moving with initial speed of UA. And that's the sphere B, mass MB, moving in opposite direction, UB. And after collision, sphere A move in opposite direction, VA. Sphere B move in opposite direction also, VB. Right? So we are just using principle of conservation of momentum. So since momentum is a vector, we have to consider taking positive direction to the right. Conservation of momentum should be able to write, right? That mass there times UA is the initial momentum of sphere A. Sphere B, right, is opposite direction, so it's negative. UB times mass of sphere B times UB, right? So that is the initial momentum. Final momentum, you look at this part. MA, opposite direction, so you put a negative sign there, right, for minus VA. And for this sphere, MB times VB. Right? So you should be able to write that equation. Then you should be able to draw the graph. Right? That's the initial momentum. Initial momentum of this one, constant, has a negative direction. Initial momentum of sphere B, negative direction, smaller. Right? This is the time of collision, which is usually very short. Right? Very shorter than what I've shown you. Right? We are looking at the same picture as the previous case. Right? That the momentum now is this is momentum after collision. Right? For sphere A, this momentum of collision. For sphere B, this is VB. So you should be able to draw that one is negative. So it's going negative. Right? That one is positive. Positive. Okay. So we can write it down. These two add together. This one minus that one. This one minus that one. Minus plus that one. That's the final momentum. Gradient give the force on the body. All collision can be classified as either elastic or inelastic collision. In all collision, total momentum is conserved. Total energy is conserved. Right? Both total momentum, total energy is conserved. In elastic collision, the final kinetic energy is always less than the initial kinetic energy. Right? Because some of the initial kinetic energy is lost as heat or sound where there's a collision, and some of the initial kinetic energy is converted to other forms. Right? So usually examiner don't like the term conserve because they don't know whether you understand what is it. Right? So it's better to say total momentum initially equals total momentum finally. In an explosion or radioactive decay, the kinetic energy after collision is greater, it's always greater than initial kinetic energy. As chemical energy, yeah, that's the explosion. Chemical energy or radioactive decay nuclear energy provides the kinetic energy. In inelastic collision, that's example of inelastic collision. Example, dropping a putty. Putty is just like plasticine or modeling clay. Collisions between bulk body, huge bodies, car and car. In general, all bulk collision, right, car and car, car and lorry. Example between vehicles are inelastic collision. As part of the original kinetic energy is transformed into internal energy as work is done in deforming the vehicle, sound, and other form. Right? So when you see a collision between two cars, they're all smashed up, the body is deformed, there's sound there, so it means kinetic energy is converted into sound. If you see spark, then there will be light energy. And then if you touch the colliding body, it's warm, so there will be heat energy, right? Internal energy or thermal energy. Okay, so this is an example of inelastic collision. Two bodies, two bodies in two bodies collision. When the two bodies stuck together, or we call couple, after collision, then the collision is completely inelastic. How do we recognize it? When the bodies stick together after collision. In elastic collision, kinetic energy is conserved. There is total kinetic energy before collision equals to total kinetic energy after collision. I stand for initial, F for final. Okay. So instead of writing all these in words, we can write in mathematical symbol. And we should be able to write for this case, kinetic energy of sphere A, ma u a square. And then if there is a sphere B, there's the velocity of ub plus mbub square. And then if that is the velocity after collision equals to final kinetic energy of sphere A half ma va square. And then if that is the speed or velocity of sphere B, right? Remember a moment, kinetic energy is a scalar, so we are not worried about the direction. We can combine the two equations. These two equations together, should be able to write this equation for this particular case. And then come to this formula, relative velocity of approach. Right? Approach means A approaching B. It's always this one approaching B. Relative velocity of separation is this one moving, right? This one moving away from this one because it has gained speed. Right? So that's why it's always this one minus that one there. Okay, but in this case, we can derive and show that that's the velocity of approach, that's the relative velocity of separation. You need to memorize in this case. They come together, and after that, they rebound in opposite direction. So you add them up together. Right? Remember, this is a vector equation. It only applies to this case. For other case, you have to think of this as these are all positive direction. Right? So we will go into that in a while. So we can derive it. This is not required in the exam. Right? You can take all the MA to one side because we don't want right? We want this equation. We don't want MA, MB in this equation. So you take this MA to that side there, MB to that side there, and rewrite the equation. And kinetic energy, the same thing. Cancel all the half there. Take the MA to this side there. MA. Okay. So if you are interested, you can just go and derive it. Okay. That one there. And this one there. Two equation. 2 divided by 1. 2 divided by 1. That's your 2. Okay. Okay, but you are required to just memorize it and then apply it to different cases. The equation is, remember, it's a vector equation that apply to direction shown. This is the direction shown. If they are in opposite direction as they approach each other, and after collision, they rebound in opposite direction to the initial direction, then you just add them all together. If the direction opposite to that shown, then it should be negative. Okay, let's try this question. This one, right? You're going to change the direction. Change the direction. So what is your answer for this case? Right, of course, this one have a longer arrow to show that in order to collide, this one must be moving faster than that one there. After collision, this one is likely to gain kinetic energy. This one is likely to lose kinetic energy. That's why it becomes shorter. This one becomes longer. Right? The right should be longer. What's your answer? Have a go. Right? That one is in the same direction. That one is in opposite direction. So that one becomes negative. Right? That one also opposite direction. So this one becomes negative. This one in the same direction. So it's positive. Okay. Same direction. Positive. Opposite direction. That one there. Negative. That one. The right direction. Is that one? But that one. This one. Opposite direction to that one. So you have to put a negative sign there. So that's the answer. In terms of magnitude, remember relative velocity tells us that the velocity the object is approaching or separating. Right? So relative velocity, this one is moving towards V2. So that's why we take V1 first minus V2. Relative velocity of approach, right, where they are coming towards each other, then V1 plus V2. Object moving in the same direction, you subtract. Object moving in opposite direction, you add them up. That's another way of looking at it. As the distance between them decreases with time. Right? The one they approach each other, this one will take a longer time to catch up with each other. Right? Just repeating. Example, elastic collision is usually in the atomic collision, atom and atom. Collision between neutrons, collision between billiard ball. This is approximate only lah. Recognize elastic collision when particle A collide with an identical stationary particle B, right? Moving with velocity UA, that one is stationary. They are same mass, identical means same mass. And this one is stationary, UB is 0. So after collision, this one stop. This one move with the velocity of A. Okay? That means this one transfer all the kinetic to this one, and then you stop. Right? Other cases of elastic collision should be identified. Right? This one is stationary after collision. Right? Same mass. This one becomes stationary. That one move the speed of this one, or velocity of that one, or approaching each other. Right? Same mass. That's a collision. After collision, this one transfer the velocity to that one there, that one transfer velocity to that one there. Or in this case there, right, same as greater velocity, smaller velocity after collision. This one transfer anything to that one transfer the velocity to that one there. Greater speed, smaller speed. Right? The one we will consider two dimension. Right? Two cars colliding. These two dimension. We will prepare a separate video for this one. Right? This allows us to investigate how the two cars are colliding and whether the one reporting the collision is telling the truth. Right? That is the initial momentum. We can draw it. Initial momentum. Okay? That's the initial momentum. Draw it as a vector. Then that's the resultant momentum. And final momentum. Okay? That's the final momentum. And there is a final momentum for F2. I want that. Both of them give the same resultant. We can measure the skid mark on the road. On the road, mass of the car can be determined. Angle of the car is moving can also be determined. Okay, we have completed. Let's try some question. Okay, have a go at this one. The diagram shows two trolleys X and Y about to collide. Momentum of each trolley before the impact is given. Right? Examiner will not give you any negative sign. Right? You are supposed to know that momentum is a vector quantity. You're supposed to put your negative sign yourself. After the collision, the trolley travel in opposite direction, and momentum of x is 2 kilogram meter s minus 1. What's the momentum of y? Right. So draw on the diagram what is given. Momentum is a vector quantity. That's important to remember. Right. This is an old question. November 88, paper 1, number 4. Choose to the right as positive is your choice. Right? So final momentum is given 2 kilogram. Right? Put a negative sign there. Put a negative sign there, yeah. Yourself. Right? We took to the right as positive, so to the left as negative. So you want to find that one there. Right? Conservation of momentum. Some momentum initially, and some momentum finally. So we add initially. Initially is these two. 20 minus 12. Final one is minus 2 plus py. So take these two across there. It becomes positive. So this one becomes 10. So its answer is 10. Answer is C. 3 identical stationary discs PQR, PQR are placed in line on a horizontal flat frictionless surface, no friction. Disc P projected straight towards disc Q. Right? Remember, identical means they have the same mass. If all the consequent collision are perfectly elastic, this elastic collision, what will be the final motion of 3 discs? Right? If memory work, this one moving with speed u collide with this one, so this one will stop. This one will move on with the with that velocity. Right? So P becomes stationary. Then Q becomes stationary. Sorry, Q P will be final one will be stationary. Q will be moving to the right. After that, it will stop. Then it transfers its velocity to R. R will move to the right. The answer is donkey. Stationary, stationary, final, final. We want final, not that it's moving. It finally becomes stationary. Right? In elastic collision, when P collide with Q at rest, P imparts all its kinetic energy to Q, and then it remains at rest. When Q collide with R, it likewise imparts all its kinetic energy to R, and it remains at rest. Right? That's for perfect elastic collision. Okay, let's have a go at this one. Two similar spheres, each of mass m, and traveling with speed v, are moving towards each other. The sphere have a head-on elastic collision. Which statement is correct? Sum of momenta, that's the plural for momentum, before impact is 2mv. Right? Which is wrong. Momentum is a vector quantity. So m times v. This is negative opposite direction. And we choose the right as positive. So this one moving to the left is minus mv. So the sum of momenta before collision is mv minus mv is 0. So A is wrong. Kinetic energy before impact is 0. Right? Kinetic energy is not a vector quantity. We just add a kinetic energy. Sum of kinetic energy before impact. Right? Both of them the same. Half mv squared. Same. So we just multiply by 2. We get mv squared. Sum of kinetic energy after collision is mv squared. Right? The two elastic collision. So it should be correct. For elastic collision, sum of kinetic after impact is mv squared. The spheres stick together on impact, giving a resultant speed of 0. Right? Sticking together, we know for sure that the collision is inelastic. The answer is C. Okay, have a go at this one. Two balls, X and Y, approach each other along the same straight line and collide elastically. Remember, it's elastic collision. Their speeds are ux, uy, respectively. After collision, they move apart at speed vx, vy, respectively. Their direction as shown in the diagram. Which of the equation is correct? Right? Remember, they are moving towards each other, so we add them up. They are moving apart, so we add them up. Right? So we use relative velocity of approach, relative velocity of separation. A. Okay. Next part, just to remind you what you have studied before, earlier, the collision, how to draw the diagram, and then how to draw the force. Force is just a gradient. Before collision, there's no force there. After collision, there's no force there. Only where they collide, there's a force during the collision. The force is constant. Okay, this is 2010 June paper 22. Two spheres approach one another in the line joining their centers, as illustrated in figure 3.1. When they collide, the average force on the sphere A is Fa, and the average force on sphere B is Fv. The forces act for time Ta for sphere A and Tb for time for sphere B. The force act for time Ta for sphere A and time Tb for sphere B. State the relationship between Fa and Fb. Make a guess. Right? You apply Newton's third law. You hit me, I hit you back. So it's the same action reaction force at collision. That's your Fa, force of B on A, force of A on B. Right? So they are the same. Newton's third law of motion. The time should be the same because they are in contact for the same number of for the same time. Right? Short period of time. Time is contact is the same. Use your answer in 1 to show that the change in momentum of sphere A is equals to the change in momentum change is equal in magnitude and opposite in direction to the change in momentum of sphere B. Okay, so we are just using that one there. Right? Remember our Newton's second law, change in momentum of time is equals to force. So replace that. Right? Change in momentum is force times time. So Fa times Ta. Right? From here, we just multiply by time. Time is the same. Okay, let's just redraw the diagram. Change in momentum equals to final momentum minus initial momentum. Okay, can write this way or that way there. Okay, let's just rewrite that. For sphere A, change in momentum is ma, right? Ma times the negative is because of this negative. That's the final one. Minus initial ma times ua. Change in momentum in sphere B, right? Final mb times vb minus mb plus ub. Right? We look at this one to find the change in momentum for this one. We look at this one to find a change in momentum in sphere A. Okay, and have a look through, see whether our calculation is correct. Right? We just left something out. Right? Positive sign. We are looking at here A is negative. This, this negative is because of our final minus initial. Right? That's the negative sign there. Okay. That's what we are doing. Find the change in momentum. That's what we are changing momentum for this one, change momentum for that one there, and is equal to FA times time A minus FB times time B. Okay, so change in momentum is this one, and change in momentum for that one there. Take the negative sign out, one negative there. Negative, take it across there, becomes positive. Yeah, declare all the initial to one side. So that is the same. There's a negative sign there. That one there. Then for this part, there's left this one. Then we can take this one, the final one, across to that side there. Becomes positive. Okay. So we are looking at this one. It shows us that this is the initial momentum for these two spheres. So check that. MB times that, MA times that. And then this is the final momentum. Right? Drag all the initial momentum to one side, all the final momentum to one side. Right? It's MA times minus VA. Right? The negative is here. There is positive, MB times VB. So there's the principal conservation of momentum. Sum of momentum of A equals sum of momentum of B. So we have shown that. Right? This is experiment we can do in the lab. Where right? This is a spring gun where I can push a ball inside there, and then it's loaded. Right? There's a spring there. When you press the trigger, the spring will be released. The ball will hit this pendulum with a catcher, and then it will swing to maximum height. We can measure it on here, that angle there. Okay, so that's a ballistic pendulum. Find the speed of the ball, initial speed of the ball. Okay, let's try this pendulum. This question. Ballistic pendulum is the device to measure the speed of the object, such as a bullet. If 5.4 gram bullet is fired horizontally into a suspended 10 kilogram block of wood, there's a block of wood, there's a bullet. If embedded means it stay inside there. To move to off with horizontal speed of 0.3 knot meter per second. Right? So intro, what is given? There's the initial speed of the bullet. There's a bullet, 5.40 kilogram. Right? So that we can know what's happening. This is not moving. Right? It has a mass of 10 kilogram. After collision, right? Embedded means the total mass is add the two mass together. We got that. Then you move on velocity. That's the velocity. What is the final momentum of the bullet? Right? So it will embedded. It has kinetic energy. So it will move up to a maximum height where all the kinetic energy change to potential energy. So we can measure this height. Right? 3 stages. Bullet stand into the block at rest. It get embedded. Total mass, it move with velocity v because it has kinetic energy. It will swing to a maximum height where the kinetic energy is 0. That's the height. Embedded means that the bullet remains in the block. So the body move off together. The final momentum of the bullet equals to the total mass times your V. Right? Total mass, refer to the previous diagram. Add the two mass together times the speed. Okay, that's the speed of the block with the bullet. That's the total mass of the block and the bullet. That's what we are doing. Conservation of momentum. Final momentum equals initial momentum. Right? That's the initial momentum for this one there. Not moving, only the bullet moving. Doing the mass for the bullet, change it to kilogram. Calculate your U. C. Right? You want to find the maximum height. So gain in potential energy equals the loss in kinetic energy. The block and bullet move to a high H before returning. Okay? So the potential energy is total mass of bullet and block times G times H. Right? Total kinetic energy of the embedded bullet is half mv squared. That's your V. G is 9.81. So dividing by m plus m. Okay, cancel that off. Right, cross multiply. Right, we get half minus speed of the bullet is that one. V 0.3. So calculate using calculator, you got 4.59 millimeter. Right, we are asked whether it's elastic. Right, let's just refer to the question again. Okay, we have found any final momentum of the bullet. We have found that. We have found what is the impact velocity of the bullet, maximum height of the block and the bullet. Then we are asked, is the collision elastic or inelastic? Okay, we have found the initial speed of the bullet. Mass of the bullet is given. Right, so you can use kinetic energy, but it's take more work to do all the calculation. It's better to use relative velocity of approach is not equal to relative velocity of separation, so not elastic. Right? Relative velocity of approach, right? That one is stationary. The block is stationary. The bullet is 550. So approach 550 minus 0, 550. Relative velocity of separation, they are stick together. Right? So relative velocity of separation is 0. That's what we are saying. Right? Moving together. So moving together, we know it's already not elastic collision anymore, or it is an inelastic collision. When an object is dropped in the Earth's gravitational field, is momentum conserved? Depends on how you view it. Right? If you say no, there's an external force of gravity acting on the object. Right? The weight is acting on the object, so there's an external force there. The speed is increasing, so it means there's an external force acting on it. So momentum is not conserved. Alternatively, you can think of it as a closed system, the object and the Earth together. Yes, as the object is moving towards the earth is also moving towards the object. So momentum conserved. Okay, let's try one last one. The diagram shows particle P traveling at speed V about to collide with a stationary, Q is stationary. Right? They have the same mass. Collision is perfectly elastic. Which of the statement describe the motion of P and Q immediately after collision? What's your answer? Right? Elastic collision for identical object, the bodies interchange velocity. Remember that. The answer is donkey. Right? P becomes stationary, stand still. Q acquire the speed of P. So you transfer the kinetic energy. That's all. This one becomes stationary. That one moves with the speed of V. Okay. So thank you for your time. We have completed our lesson.